Hey, welcome back to my channel. In this video we are going to talk about the remaining reaction of benzenes that is going to serve as a part 2 of my previous video on the organic chemistry playlist. Let's start with nucleophilic aromatic substitution that is not as common as electrophilic aromatic substitution, but it occurs under two conditions. You should have a halobenzene, and this halobenzene should contain electron withdrawing groups in ortho or para position. Like in this case, for example, a halogen is connected to the benzene ring and it contains a nitro group at the ortho position. Nucleophile is going to attract to the electron deficiency aryl halide, and this double bond is going to move here to form a carboanion intermediate. And after the elimination of chlorine, you have the remaining substitution of the nucleophile. This mechanism, as you can see, is not as SN1 mechanism that you have the carbocation formation as an intermediate step, or as an SN2 mechanism that the nucleophile has to attack to the back and to reverse the configuration. It's different, okay? Let's move now to benzyne. Benzyne is a triple bond benzene, as you see. As we learned above, we can carry out a nucleophilic attack if you have a halobenzene and electron withdrawing group in ortho or para position. But if you carry it out under high temperature and very high pressure, you can yield phenol. But this method is industrially used and is discovered in 1928, early times. But if you carry out with potassium amide this reaction in ammonium solvent, you can form aniline. And if you label here carbon 14, a radioactive carbon, it is observed that you have a symmetrical formation in both positions. But this compound is not as stable. Even if we treat this compound with water, it's going to form phenol, okay? Let's move now to the oxidation of the aromatic compound. You can use a powerful oxidizing agent that is not going to impact the benzene ring. You can use potassium permanganate, potassium dichromate. You want an oxidizing agent, and it's going to break this bond here, and you're going to have the formation of a benzoic acid. Okay? Keep in mind that this mechanism, that I'm not going to show the details, it involves the hydrogen that is present at the benzylic position. If you have this compound here that does not contain hydrogen in the benzylic position, this reaction does not occur. Let's move now to the bromination of the alkyl benzenes. If you use N-bromosuccinate that we use to the alkanes, in the presence of benzoyl peroxide, that is an initiator of the radical reaction, you can brominate at the benzylic position. At this position here, you can add bromine. Keep in mind this reaction. Let's move now to the reduction of aromatic compounds. There are several methods to carry reduction. If we carry a normal reduction that we did with alkenes, with hydrogen, palladium, and ethanol, take a look at this compound that contains benzoic ring, it contains double bond and carbonyl group. You can see that only the double bond is reduced, so it's so selective. But if you try it with hydrogen in platinum catalyst and at higher pressure, you can convert the benzene into cyclohexane. And keep in mind that two hydrogens adds on the same side, so we form a cis product. But it's very high pressure, 130 atmosphere. But if you change the catalyst, for example, if you take hydrogen with rhodium on carbon, at 1 atmosphere you can reduce the benzoic ring and converting that to the cyclohexane. So keep in mind, if you use hydrogen palladium, you're going to eliminate the double bond if you have a double bond, but you are not going to touch the benzoic ring. But if you use hydrogen in rhodium on the carbon, you have the reduction of the benzoic ring. This is the difference. Or otherwise you have to use high pressure. Okay, the last one that I want to mention is reduction of aryl alkyl ketones. If you remember from my previous video, you can carry out Friedel-Crafts reaction both ways, but on the second way that you add directly the alkyl halide, you have the carbocation rearrangement here. But if we carry it out under acyl chloride, you do not have that phenomenon. So this carbonyl group is going to be indicated by the benzoic ring, and if we treat that with hydrogen and palladium, you are going to have the reduction of the carbonyl group and formation of primary benzoic halides. Keep in mind that this happens only if this carbonyl group is directly attached to the benzoic ring. If it's like in this case, that is far away, you do not have this kind of reduction. So in order for that to happen, it should be connected to the benzoic ring. Be careful, do not confuse this. Feel free to pause the video at this moment and try to find those reagents by yourself. Okay? Did you pause that? Okay. Okay, let's move to this exercise. Practice makes you perfect, as you know, especially with organic chemistry. At point A, as you may guess, it should be a Friedel-Crafts reaction by including the acylation. The second step, you have reduction of the carbonyl group that is connected straight to the benzene. So in this case, you can use easily the hydrogen in palladium. Okay? You can add also ethanol as a solvent to complete. Now, from here, that you form a primary benzene halide, here you have to go here. So in order to add bromine here at para position, you can use bromination reaction, that is a characteristic electrophilic substitution to the benzoic ring. So let's move further. Here you have bromination at the benzyl position. So here you have to add the N-brom succinate that we learned above in the presence of benzoyl peroxide. Now let's move to the last step. Here you have formation of the double bond. Now here is from alkene reactions. You can check that video if you want. So here you have you need an elimination reaction that you can use. Let's write it here. Potassium hydroxide in ethanol. Okay? Thank you so much for watching, and look forward to see you at the part 3 of this video. This is going to be only the exercises now, with what we have learned so far. Bye!